So a three-port device that's matched, lossless, and reciprocal is not possible since the scattering matrix that would result cannot exist mathematically. Although it turns out a two-port device can exist that's matched, lossless, and reciprocal. It's kind of a trivial one, but there is one that exists. The question then becomes, is there a four-port network that is matched, lossless, and reciprocal? And it turns out there is. There are scattering matrices, or matrices, 4x4 matrices, that will be symmetric and unitary, and will have zero value diagonal elements, and therefore we can build, it is possible to build a four-port device that's matched, lossless, and reciprocal. And so let's look at the what the scattering matrix for such a device would look like. So there's actually two general solutions for a scattering matrix of a four-port device that's matched, lossless, and reciprocal. The first of these solutions is referred to sometimes as the symmetric solution. I prefer it wasn't named that because we'll find later that the scattering matrix of a device will say much about the physical symmetry of the structure inside of it. And so in this case, this symmetric is different than describing the physical symmetry inside of it there. But nonetheless, this is what this solution is called. If you look at this, we find that there are essentially four values that are have permutations in order across each of the four columns of the scattering matrix. And those four values are alpha, j, beta, and then two zeros. And every column has an alpha, a j, beta, and two zeros. Now, strictly speaking, alpha and beta can be complex numbers. For the most part, though, we typically write this in terms of alpha being and beta being real values, although they, strictly speaking, don't have to be mathematically anyway. So this is one solution. We see that it's matched, the diagonal elements are equal to 0, and see that it is symmetric, the result, and you can go through and show that the columns are orthogonal to each other given another constraint on both alpha and beta. And so let's look, we'll see that constraint here in a second. So the second solution is what's referred to as the anti-symmetric solution. And in this case, again, we have four values that are permeated across each of the four columns there. In this case, alpha and beta, no j involved here, and then two zeros. When we go to the next column, notice we have alpha and minus beta, however. So we have a minus sign here. So it's not exactly the same. We go from beta to minus beta, and then minus beta back to beta, and then beta back to minus beta again. But alpha shows up in each of the columns, and then beta or minus beta shows up in each of the columns as well. The other two elements are 0. Again, the diagonal elements here are 0. It's symmetric, and it is unitary. Given a constraint on both alpha and beta, as we'll see. Mathematically speaking, alpha and beta can be complex, but generally we write this such that alpha and beta are real values. So I pointed out that both solutions, symmetric and anti-symmetric, were clearly matched diagonal elements of 0 and reciprocal, a symmetric matrix. With respect to lossless, though, it is true only if the columns are orthonormal, if we have a unitary matrix. And when we look at this, we see that, of course, the columns need to be have a magnitude of 1. And if we do that for every column in the symmetric case, it results in precisely the same equation. Since we have alpha and a beta and two zeros, when we take the magnitude of the columns, we find every column is the same, and therefore every column has a magnitude of the magnitude squared of alpha plus the magnitude squared of beta. For this to be a unitary matrix, that magnitude must be equal to 1. So I'm not saying that the magnitude of alpha plus the magnitude beta is squared is equal to 1. I'm saying it must be equal to 1 if we are to have a lossless device, if our device is to be unitary. If we go and do the same thing for the anti-symmetric case, we get the same values. Of course, when we get a minus beta and we square it, we get then the same value of magnitude of beta squared. And so this is a constraint that puts on the value of alpha and beta. Again, alpha and beta could be complex, but generally speaking, we write this such that alpha and beta are real values, actually positive real values. So this then completes our solution of a 4-port device that is matched, lossless, and reciprocal. It will have a scattering matrix of one of two forms, a symmetric or asymmetric form, and the values of alpha and beta in those solutions must be constrained by this result. The magnitudes, sum of the magnitudes squared of each must be equal to 1. Again, alpha and beta could be complex. Generally speaking, we set alpha and beta not only to be a real value, but also a positive real value. Moreover, it is defined such that the magnitude of beta is the smaller of the two. They could be equal magnitudes if the magnitude squared of each were equal to 0.5, and that oftentimes happens. But if one of the values, magnitude squared, is greater than 0.5, then the other one must be less than 0.5. And in that case, the smaller of the two values is assigned to beta. So beta, the magnitude beta is somewhere between 0 and 1 over the square root of 2, and the magnitude of alpha is the larger value. It is set such that it's a value somewhere between 1 over the square root of 2 and 1. We look at this and we could have a situation where, again, the magnitude squared of each alpha and beta are 0.5 and therefore add to 1, but we could have a situation where beta could be very small, 0.1 for magnitude squared, and therefore alpha would have a value of 0.9, or 0.01 squared for beta, or 0.0001 squared for beta. These are actual devices that are useful to us, and so oftentimes we will see the magnitude squared of beta to be that small.